All right, I didn't hear any complaints about the circles, but the parabolas are what I got a few questions about. One problem, I think it was number 10. No, that's number 10. Number 8 asked a question about focus and directrix. We didn't mention those characteristics of a parabola in class, and you really didn't have to know anything about it to get this problem right. So just don't worry about focus and directrix. It's the only problem I forgot to take those words out, but you could still look at that y squared equals 36x and know that it was a parabola that had the vertex 0, 0 and open to the right. That's all you needed to do to pick A, B, C, or D. So I'm not worried about that one. Some of the others, let's see. Just work that out on paper real quickly and let me see. I want to do a sideways one. That's not a sideways one. That one would be. All right. So y squared minus 3y minus x plus 4 equals 0. Ooh, this is a good one. Let me go ahead and work it out so that you can see what the vertex is and then tell you the best way to graph it in my math lab. As far as test is concerned, what I said in class is absolutely true. If you have a sideways parabola that opens to the right and has the right vertex, that's all you're going to need for the test, and that's fine. I just forgot that in my math lab you do have to get the one other point to determine the width of the parabola in order to get it right in my math lab. So this is the problem that I copied down from the homework. How do I know it's a parabola and not a circle? Only one variable is squared, so I know it's a parabola. And does it have a vertical vertex or a horizontal vertex? I don't mean vertex, I mean axis of symmetry. It's a horizontal parabola because it's the y that's squared rather than the x. So to get that in a form that I could see the vertex, I would get the y's on one side and everything else on the other because I need to complete the square on the y's to see the vertex. What would I have to add to this left-hand side to complete the square? Man, I don't like to think of that as a decimal. You're right. Half of 3, I'd rather just leave it 3 over 2, and then I can square it in my head. 3 halves squared is 9/4, so I would add 9/4 to the left, and then, of course, I'd have to add 9/4 to the right. But that is 2.25. It just more obviously came off of your calculator than out of your head. That left-hand side would factor into y minus 3/2 squared. And the right-hand side would clean up to be negative 16 plus 9 is negative 7/4. And then to have it in vertex form where you see the vertex, you need to solve for that first degree variable by adding 7/4 to both sides. And I just flipped it around so the x would be on the left and everything else would be on the right. All right, be very careful. Tell me the vertex of that parabola. You're right about the positive 3/2. But what about that 7/4? That's, yeah. The vertex is 7/4 3/2, and why is it in that order? When I said be careful, what are you being careful of there? We're used to saying the opposite of the guy in parentheses and the guy on the end, but this guy in parentheses is with the y, so it's the y coordinate of the vertex. Now, that's when I go to graph it, that's 1 3/4 and 1.5. So going back to my math lab, I know it is a parabola which opens to the right, so I'm going to click on sideways parabola, and the vertex 1 3/4, 1.5. Look at this ordered pair changing down in the right-hand corner right above the blue box. That's what I need to watch until I get it on 1 3/4 for the x and 1.5 for the y. 1 3/4, 1.5 right there. You see those coordinates, 1.75 and 1.5? That's the vertex, but I do have to have another point to know how wide this parabola is. How can you get any other point on any graph? Any, many, miny, mo, either let x be something else or let y be something else. All right? All the ordered pairs on a graph are solutions of the equation. So if I just look at that, see if I can drag this down, look at that equation, it would be a whole lot easier to let y be something than x. If I let x be something, I'm going to have to solve for y. If I let y be some other number, I'm just going to have to substitute it in. What if I let y be maybe, what if I let it be 3/2? Any, miny, miny, mo, let y be 3/2. Because then it would be easy to calculate. 3/2 minus 3/2 is 0. 0 squared is 0. 0 plus 1 3/4 is 1 that's the same thing I just got. I'm sorry, play like that didn't happen. Yeah, that's the same point as this. That's how I got the vertex. So that's not a good thing to let y be. Let y be 0. Let y be 0 if you want to. Then you would have negative 3/2 squared is 9/4. 9/4 plus 7/4 is 16/4, better known as 4. So the point 40 should be on that graph as well. Let's see, 40 right there. So just let x be something else or let y be something else. All you have to do is get one other point on the graph, and my math lab will give you credit for that. Any other point on the graph. I could have let x be 1 or let y be 3. All right. Notice that in my math lab, I don't have as an option for graphing an ellipse or a hyperbola. So that's why tonight's homework is in momentum and more like it will be on the test. Of course, the test is on paper, so having assignment 16 on paper will help prepare you for that better than doing something else in my math lab. All right. Ellipses and hyperbolas. The two conic sections that we've talked about so far are circles and parabolas. And I mentioned that you don't have to learn, two different forms of an equation for each of the 4 different conic sections. You don't have that much to memorize. How do you identify a circle without memorizing center radius form or general form? Beautiful. Both variables are squared. Now you'll see that that's true for ellipses and hyperbolas as well. Parabola is the only conic section where not both variables are squared, but circles are different than ellipses in that they have the same positive coefficient and ellipses have different positive coefficients. A circle is a circle because when you graph it, you plot the center and then you go out in every direction the same distance. If we found the radius to be 2, you'd plot the center and then go left 2, right 2, up 2, down 2, connect the dots. And so all the points on a circle are equidistant from the center. Ellipses are like circles that somebody sat on. They would be, oval would be a non-mathematical term for an ellipse, but you just don't go the same distance left and right as you do up and down, and that's why you get not a perfect circle, but rather an ellipse. An ellipse is the set of all points in a plane. The sum of whose distances from 2 points is constant. Each fixed point is called a focus of the ellipse. In other words, when I graph an ellipse, and I'll just, for an example, use one that has center at the origin. There are 2 points inside an ellipse called the foci of the ellipse. And if you take any point on the ellipse and add the distances to each foci, that sum would be the same for any point on the ellipse. I could take a point way over here and add the distances to each focus, and that sum would be the same as that sum. Now that's the definition of an ellipse. You don't really have to worry about it. You have to identify it, and you have to pick out what you need in order to graph the ellipse. To graph the ellipse, you need to know 3 things. The center, just like a circle, and then instead of radius, which is that distance you go in every direction, for an ellipse, you're going to have a direction that you go to the left and right, and then a different direction that you go up and down. Look at this equation of an ellipse. If I just covered up that a squared b squared in the denominator, that would just be the equation of a circle. Both variables would be squared with the same positive coefficient. That would be a circle with center HK and radius what? No. This is the equation of a circle. What's its radius? Square root of that constant on the right-hand side, it would just be 1. This would be a circle whose center was HK and whose radius is 1. But for an ellipse, the x minus h squared is over something and the y minus k squared is over something. The a tells you the distance to go to the left and right. The b tells you the distance to go up and down from the center. So for example, number 18, you might be thinking, well, the x and y are both squared and they both have a coefficient of positive 1, but really you could write this first term as 1/25 x squared plus 1/4 y squared. That would mean the same thing, and that's why the x and the y don't have the same coefficient. The coefficient of this x squared is 1/25. The coefficient of this y squared is 1/4. That's why it's not a circle. Why is it not a parabola? Because both variables are squared. Parabola only has one variable squared. So it's an ellipse. If I just covered up that 25 and 4, you would say this is a circle with center what? 0, 0, because you don't have that guy in parentheses with the x and the y that would indicate a horizontal or vertical shift. So if I covered up the denominators, you'd say that's a circle with center 0, 0 and radius 1. Well, the center is still 0, 0. But a, notice a squared is in the denominator of the x term. A squared is 25. That means a is 5. And b squared is in the denominator of the y term. So b squared is 4. That means b is 2. So to graph that ellipse, just plot the center at 0, 0. Go to the left 5, to the right 5, up 2, down 2. That's an ellipse that's wider than it is tall. How could I have told from the original equation that it was going to be wider than it was tall? The A was bigger than the B. The A tells you how far to go left and right. The B tells you how far to go up and down. So if A is bigger than B, it's going to be wider than tall. If B is bigger, it's going to be taller than wide. All right. One other thing about this equation of an ellipse, I could clear out the fractions. I could multiply x minus h times x minus h and y minus k times y minus k and combine like terms and get it all set equal to 0. I could do that. It would be general form of an ellipse, just like we have general form for a circle. I don't want to do that, though. This form is the form that you need an ellipse in order to be able to see the center, the A and the B. And in order to see that, you have to work until you get a 1 on the right-hand side. Now, number 22, we don't have that 1 on the right-hand side. I can tell that it's an ellipse. I can definitely tell it's not a parabola because both variables are squared. It's not a circle because both coefficients are positive but not the same. That's what tells me it's an ellipse. But how can I get it in this form that has a 1 on the right-hand side? Yeah. I thought somebody might say subtract by 17, and that would work, not subtract by, but subtract 17 from both sides. That would be a way to get a 1 on the right-hand side, but it would mess up the whole problem. It's easier just to divide both sides by 18. When you simplify that, you have x squared over 18 plus y squared over 2 equals 1. And now I can see that the center of that ellipse is what? 0, 0, because you don't have those guys in parentheses. It hasn't been shifted horizontally or vertically. The center is 0, 0. What is A? Square root of 18. Square root of 18, which is 4 point something, about 4 1/4, darn close to 4.25. I can't be that accurate graphing anyway. I'm just going to say about 4.2. And what is B? The square root of 2, whatever's under the y's, the square root of 2 is about, I thought it was about 1.4. Does it round up to 1.5? 1.4. Okay, so about 1.5. All I have to do to graph that ellipse is plot the center, go to the left and to the right just a little over 4. Up and down about 1.5. Any questions? What's different about 44? Yeah, its center is not at the origin. What is the center of this ellipse? Good. You took the opposite of both guys in parentheses like we always have. That ellipse is shifted to the left 4 and down 2. What is A? Square root of 9 is 3, and B is 2. Center at -4, -2. Go to the left 3, to the right 3, up 2, and down 2. Have any of you ever visited Washington, D.C. and saw the ellipse? Do you remember seeing the ellipse in D.C.? I was there a couple weekends ago, and it was going to be the highlight of my trip, and I missed it somehow. Does anybody know what I'm talking about? Have you seen that on a map, a walking map of D.C.? There's an area, and I thought it was a room in the White House or Capitol, and it's not. It's an open area on the map. It's a field that's called the Ellipse, and there's these 2 points, the foci of an ellipse are such that 2 people can stand on the foci of the ellipse and hear each other whispering. I don't even know how that could happen outside. That's got to be a room that's elliptical so that the sound is bouncing off the walls. See, gosh darn it, I missed. It was going to be a great example for the rest of my teaching career, and I missed it on the map. 2 people standing on the foci of an ellipse can whisper and hear each other because of the way that sound waves bounce back and forth around in the ellipse. Nobody around, nobody other than the person standing at the other foci can hear them. Man, I'm going to have to go back to DC. Let's make it what? Yeah. And not only that, Rome State has those wonderful travel abroad trips. I went on the European tour a couple years ago and visited all kind of World War II sites in Europe. I've been wanting to have put together a trip for me to lead. That was led by a history professor. I've wanted to lead a trip abroad, but I have 2 problems. Number one, you have to lead a trip that has an emphasis in your discipline. And so I can't think of a good math trip. And the second problem is I don't know who would sign up for it. Maybe DC, maybe we could go to the Ellipse in DC and that be the whole trip. I don't know. You can do that. Yeah, I know. And on this European trip, we saw some phenomenal Roman architecture. Point du Gard is one of the Roman aqueducts, and it's so incredible. We could go there and study. Yeah, we could go there and study the math of the Roman aqueducts. Gosh darn it. There are some limitations to my field. No good field trips. To the what? To the collider? That's scary. I could. I was there. And I didn't. Gosh darn it. What was I thinking? Okay. And 2 ellipses with center 0, 0. One whose center is not 0, 0, but still it was easy to find the center because it was in that beautiful equation with the 1 on the right-hand side that I could just look at it and see the center and the ellipse. And then you know what's coming. One that's in general form, and we have to complete the square. But that's okay. We learned to complete the squares for circles. We should be able to do the same thing for ellipses. Just like I did for circles. Ooh, let me back up. How do I know this is not a parabola? Both variables are squared. How do I know it's not a circle? The coefficients are both positive, which, by the way, will tell us it's not a hyperbola when we get there. Both variables are positive but have different coefficients. That's why it's not a circle. So therefore, it's an ellipse. But to see the center and the A and the B, I'm going to have to complete the square. Just like I did with my circles, I'm going to group the X's, group the Y's, subtract 4 from both sides, getting ready to complete the square. Now, we encountered this in section 2.4, a problem that I have to take care of before I can complete the squares. What's the problem I need to take care of? I need the coefficient of y squared to be 1 before I can complete the square. So I'm going to just factor a 4 out of that second parentheses. And you can check every step of the way. Every line should be equivalent to the line above it. If I redistribute that 4, I have exactly what's on the line above it. And then I'm trying to think of what's easiest to do next. For reasons you'll see in just a minute, I'm not going to divide by that 4 yet. That's different than I would have done with circles, but circles, these 2 coefficients outside parentheses were the same. So I could divide by that coefficient and just have coefficients of 1 on the left-hand side. Right here, if I divide by 4, that's not going to have an integer coefficient anymore. It's going to be 1/4. So I'm going to leave it alone, and you'll see why in just a second. Tell me what to add to complete the square on the x's. Half of 4 is 2, and then square it, you get 4. So x squared plus 4x plus 4. And if I add 4 to the left, I have to make sure to add 4 to the right. What would I have to add to complete the square on the y's? Half of 2 is 1. 1 squared is 1. If I add 1 to the left, I also have to add 1 to the right. But I didn't really add 1 to the left. I added 1 inside the parentheses, but everything inside the parentheses is multiplied by 4. So I really didn't add 1 to the left. I added 4 to the left. That's why I have to add 4 to the right. You really have to watch out for that. If you have any coefficient other than 1 in front of that parentheses, you have to take that into consideration when you're balancing it by adding something to the other side. If there's something other than a 1 there, then you really didn't just add what's inside parentheses. You added that times that coefficient. All right, that was the hard part. this first term, this first perfect square trinomial factors into what? X plus 2 squared plus 4 times, what does that second perfect square trinomial factor into? Y minus 1 squared, because you kept the middle sign, and the right-hand side cleans up to be negative 4 plus 4 is 0, plus that other 4 is 4. All right. One other step, I don't yet have it in the form with the 1 on the right-hand side, but all I'd have to do is what? Divide both sides by 4. And I have x plus 2 squared over 4 plus y minus 1 squared over, ooh, what's that over? Yeah, sure it is. 4 goes into 4 one time. Just put a 1 in the denominator if you want to. And there's my 1 on the right-hand side. So what's the center of this ellipse? Negative 2, positive 1. Opposite of both guys in parentheses. And the A is 2 and the B is 1. So very quickly to graph that, just plot that center at negative 2, 1. And then go right 2, left 2, up 1, down 1. I think you have 4 ellipses to graph in your homework. And from the book, they're probably, number 19 is just like 18, 23 is probably just like 22. Then you probably have 44 and 48. Mr. Caleb, when you emailed me this weekend, did you go back and look at the problem that I emailed back to you and answer it? You got it after you looked at it? Okay. All right, because I'm really trying, I know this is new to most folks, and I'm trying to do an odd problem just like every even problem in your homework. So make sure you look at those if you get stuck, for example, on 40. Well, that is 47, so you must have to do 45 in the homework. All right, that's all I need to say about ellipses. And just when you think math can't be any more fun, you get hyperbolas. A hyperbola is the set of all points in a plane. The difference of whose distances from 2 fixed points is a constant, and those 2 fixed points are called foci, just like they were for an ellipse. An ellipse, these 2 points inside are the foci, and you can take any point on the ellipse and add the distances to those 2 foci, and you get the same sum for any point on the ellipse. For a hyperbola, the distance from the difference of those 2 distances is the same for any point on the hyperbola. I mentioned that hyperbolas look like a pair of parabolas, but they're not. They have a whole different set of properties, and the properties of a hyperbola are such that meteorologists use them to pinpoint lightning strikes. I don't know how because I've never been trained as a meteorologist. I just know that that's one application of hyperbolas. An application of parabolas is a parabolic antenna. during a football game. I'm trying to think if this, oh, speaking of football games. Oh, that was good. Lord of mercy, my husband went crazy. Is there still the guy on the sidelines holding a parabolic antenna, or is that outdated? They still have a guy running around with an antenna? Yeah, it's about this big instead of a dish satellite. The properties of a parabola make it the best shape for receiving and transmitting sound waves and light waves. That's why the dish on your house, if you have DirecTV or Dish Network, the cross section of that satellite dish is a parabola. If you cut your contact lens, which I recommend you take it out of your eye first, but if you cut it when you're through with it, the cross section of a contact lens is a parabola because it's the best shape for capturing those light waves, transmitting them to your retina, and then whatever else happens after that. So again, there are a lot of applications. God knows conic sections. They weren't invented by Euclid. They were just discovered. All right, what do you really have to know? You have to know how to recognize a hyperbola, and you recognize them because like circles and ellipses, both variables are squared. But if one of the variables has a negative coefficient, then it's a hyperbola. Hyperbola is the only conic section that either the x squared or the y squared will have a negative coefficient. The equation looks a lot like an ellipse. If that was a plus in the middle, it would be an ellipse. It'd be an ellipse with center HK, and the A would still give you the distance left and right. The B would still give you the coefficient, or the distance up and down from the center. You still have to get a 1 on the right-hand side in order to get that important information you need to graph a hyperbola. Because a hyperbola looks like a pair of parabolas, it can either open up and down, or it can open left and right, and you can tell which way it's going to open by which coefficient is positive. If your x square has a positive coefficient, then it opens left and right. All things x's have to do with leftness and rightness. So if your x square is positive, that hyperbola is going to open to the left and to the right. If it's your y square that's positive and your x square has a negative coefficient, if it's the x that's subtracted, then your hyperbola is going to open up and down. For example, number 30, how do I know it's not a parabola? Because both variables are squared. That's why it's not a parabola. How do I know it's not a circle or an ellipse? One of the squared terms has a negative coefficient, therefore it must be a hyperbola. And it's in that perfect form where I can just look at it and tell you that the center of this hyperbola is what? 0, 0. There's no horizontal shift or vertical shift. Does it open up and down or left and right? Look at the coefficient that's positive. The y squared has a positive coefficient. If the y squared is positive, it opens up and down. Be careful. What do you think is A? Yes, it's under the x's. A is always the square root of the constant under the x's. B is always the square root of the constant under the y's. So A is 2, B is 4. Now, got it? All right. This is the most fun you can have without a quart of ice cream. Center is 0, 0. Left 2, right 2. Up 4, down 4. If I just connected those 4 exterior points right now, I'd have an ellipse, right? This is not an ellipse. To graph a hyperbola, and this only takes a little bit of practice, can you see a rectangle that is this wide and this tall? Can you see where the corner points of that rectangle would be? Don't draw this on your paper, but I'm trying to get you to visualize that rectangle. You plot the corner points of that rectangle. That rectangle is called the fundamental rectangle of the hyperbola, and you plot its corner points. It's going to be the same width as your A's give you and the same height as your B gives you. Those are the corner points of the fundamental rectangle. And then you dash in the diagonals of the fundamental rectangle. You know what a diagonal of a rectangle is? Just dash it in. Ooh, play like I hit that point. Here's the coolest sentence in all of math. The diagonals of the fundamental rectangle of a hyperbola are the asymptotes of the hyperbola. I think that should be the final exam. Can you say that sentence? The diagonals of the fundamental rectangle of a hyperbola are the asymptotes of the hyperbola. That means the line that the graph gets closer and closer to. Like when we graphed 1 over x, it had asymptotes and the graph just kept getting closer and closer to those asymptotes. The graph of the hyperbola is going to get closer and closer to these asymptotes. And we've already determined that it opens up and down. So it goes through these 2 points on the y-axis and gets closer and closer to the asymptotes. There's the bottom. Yeah, I wasn't supposed to touch. That was a oops on my part. There's the bottom part of the hyperbola and the top part of the hyperbola. And it does look like a pair of parabolas, but it is not. Just the littlest bit of practice, and you can do these in your sleep. Just plot the exterior points, or plot the center, then count left and right A, up and down B, put in the corners of the fundamental rectangle, and then dash in the diagonals. By the way, if we had determined that this opened left and right, look up for just a second. If this opened left and right, it would be going through these 2 points on the x-axis rather than those 2 points on the y-axis. And we'll have an example of one of those. Any questions? All right. Let's do another one that's not quite in that form where I can just look at it and see the center, the A, and the B. What's the only thing I would have to do to have it in that form? Get that 1 on the right-hand side by dividing both sides by 16. The first term simplifies to x squared over 4. The second term stays y squared over 16. And there's the one that you need on the right-hand side. So what is the center of this hyperbola? Yep. 0, 0, because there's no horizontal and vertical shift. A is square root of whatever's under the x's. A is always under the x's. So square root of 4 is 2. And B is the square root of the constant under the y's. That'd be the square root of 16, which is 4. Only other thing I need to know before I graph is, does this hyperbola open up and down or left and right? It's the x squared that has a positive coefficient, so it opens left and right. All right, here we go. Just like an ellipse, plot the center. And then go left and right 2, up and down 4. I need the corners of the fundamental rectangle. The rectangle that's 4 units wide and 8 units tall and has the center 0, 0. Can you see where those corners would be? 2, 4, negative 2, 4. You don't even have to say them. Just they're hard to say. Just plot them. Can you see them? If you can see them, plot them. And then what? Dash in the diagonals. And then finally, make sure your hyperbola opens left and right, because the x squared had the positive coefficient. That means it's going to go through these 2 points on the x-axis and approach those asymptotes. Any questions? Trying to think why I felt like we needed another one of these. Number 36 is just like 31, has a different A and B, but the steps are the same. You have to divide by 4 and then pick out the A and the B. It even opens left and right. So it's just like 31. Let's not do that one. Let's go to number 50. And I had mercy on you. You're not going to have any hyperbolas in general form where you have to complete the square to get the center, the A and the B. All the hyperbolas in the homework are already either they already have a 1 on the right-hand side, or it just takes one step to get the 1 on the right-hand side, but you don't have to complete the square. So number 50, be careful about order. What is the center of this hyperbola? The 2 is with the x, the 3 is with the y. It's still the opposite of both guys in parentheses, but make sure you have them in the correct order. 2, negative 3. And be careful picking out your A's and B's. A's always the square root of what's under the X's. So A is 3 and B is 2. And this hyperbola opens how? The y squared had the positive coefficient. The x squared had the negative coefficient. So it opens up and down. Center at 2, negative 3. Left 3, right 3, up 2, down 2. If I connected those 4 exterior points, then I'd have an ellipse. But to get a hyperbola, I need to plot those corners of the fundamental rectangle. Dash in the diagonals. And then this hyperbola is supposed to open up and down. So just go through the 2 points that were determined by counting up and down from the center. Any questions? All right. Your test is Wednesday. Assignment 16. Let me just show you what that looks like. I've printed the first page off Momentum. Because I'm trying to get you ready for the test, there are a couple of ellipses to graph from section 7.3, a couple of hyperbolas to graph from 7.4, but the next page, actually I didn't print the next page, it has some circles and ellipses also for review, and then there are some that just say identify. Man, I wish I'd brought those other 2 pages. Do you have them? Let me show you just the last page. That one. And I gave you the answers, so you just have to be a knucklehead not to make 100 on this assignment. But I'm trying to get you ready for the test, and it doesn't do you any good to do 12 problems and not know if they're right or wrong, so I had to give you the answers. This last page, 9 through 12, those are all mixed up. Let's see if we can identify them. What does number 9 have to be? Hyperbola. Can't be a parabola because what? Both variables are squared. Can't be a circle or an ellipse because what? One of the coefficients is negative. One of the coefficients of the square terms is negative. Therefore, it must be a hyperbola. Number 10, definitely a parabola because only one variable is squared. You may just have to complete the square to have it in center radius, not center radius, have it in vertex form where you can see the center and so you can see the vertex. What about 11? Can't be a parabola because, well, yes, but that's not why it's not a parabola. It's not a parabola because both variables are squared. It's not a circle because different coefficients, and it's not a hyperbola because both coefficients are positive. Therefore, it's an ellipse. And then number 12, can't be a parabola because both variables are squared. Can't be a hyperbola because the x squared and y squared both have positive coefficients. What is it? Circle because both variables, both square terms have the same positive coefficient. All right. I want to remind you of, thank you, ma'am. One other, yes, you turn that in for your homework score Wednesday before the test. And I'll get here early. What if I come at 9:45 like I did for the last test, just in case you need extra time? I'll be in here at 9:45 and you can have until 11:30. That gives you an hour and 45 minutes. It shouldn't take you that long. Let me think of a few other things that No, there is no assignment 16 on my math lab. It's strictly on paper. All right. Something else. Oh, I know where it is. What's the best thing to show you? We have a few minutes, so let me see what I can say that might possibly be helpful to you in preparing for the test. In momentum. Remember, you have the My Math Lab practice test that counts as part of your course grade. So do that until you can make at least a 90 blindfolded. But then as optional extra practice, and I think it's pretty important to practice something on paper just because it looks more like the real thing than the one in My Math Lab. So I've posted this practice test 3 in momentum. And this is a darn lot like the test. Number 1 and 2 were from section 4.3, where we learned to give a lot of details about a parabola. Number 1, you can just look at it and see the vertex. Let me fix this. Nope, that's not what I want. Trying to make, that was not good. That's better. All right. Number 1 and 2. Let's just run through some things we're supposed to remember. Number 1, you can just look at it and see the vertex is what? -3, +2. Number 2 is not in that same form. How do you find the vertex of a parabola that's not given to you in vertex form? You could use the little formula -b/2a to find the vertex. That's what you have to use on number 2. Either use -b/2a, or now that you know completing the square, you could do that, but -b/2a is easier. Make sure that when you give me the axis of symmetry, you give me the equation of a line, not just a number. On number 1, since that vertex is -3, +2, what's the axis of symmetry? X equals, and it has to go through the vertex, so x equals -3. What's the domain of any quadratic equation? All real numbers are negative infinity to infinity. The E part range, graph it first, and then just give me the lowest Y value to the highest Y value. In the F part, how do you find a Y-intercept? Let X be 0. And in the G part, how do you find an X-intercept? Let Y be 0 and solve that equation. H part, extreme value. Would a concave up parabola have a maximum value or a minimum value? Concave up would have a minimum value at the vertex. Now, for that minimum value, you give the Y value of the vertex. So in number 1, the Y equals 2 would be the minimum value of that function. Number 2, I can't tell what the Y value of the vertex is without using negative B over 2A, so I'm not going to do that. Then you have one word problem that's very similar to number 3 or number 4. Both of those are quadratic equations, so their graphs are parabolas, and you're asked to find something about the maximum. Where does the maximum of a parabola occur? At the vertex. Both of them are concave down parabolas, so they do have maximum values, and they're at the vertex. So I could take all the words out and just say, find the vertex, and that would be the same question as number 3. It doesn't matter if it's about a ball thrown up or tractors thrown down or what. If it's find the minimum or maximum value of a parabola, it's just find the vertex. The x-coordinate in number 3, the x-coordinate would give you the number of seconds the ball takes to reach its maximum height. Once you find that number of seconds, you plug it back in and you find the maximum height. Same thing with number 4. Find the vertex, the x-coordinate would give you the price, and the y-coordinate would give you the max revenue. Number 5 and number 6 are just graphed based on what you know about higher order polynomial functions, whether the degree is even or odd, whether the leading coefficient is positive or negative. That's all you need to graph the A and B parts of number 5. Number 6, you need to know same thing, odd or even degree, positive or negative coefficient, but also you need to know how the graph has been shifted in number 6. Number 7, that was 5.1. And remember, you did part of that homework on paper, and I'd made you a beautiful little table. Give me the end behavior, the y-intercepts, the zeros, their multiplicity, and whether the graph crosses or touches. That's what number 7 is. Any zero with even multiplicity, the graph does a U-turn there. Any zero with odd multiplicity, the graph crosses the x-axis there. And then 8 and 9 are both from section 5.5. You have 2 identical to that on the test. Remember number 8, part A, the possible rational zeros. That's where you list your factors of the constant, your factors of the leading coefficient, and all possible combinations of factors of 6 over factors of 2. Those are your possible rational zeros. In the B part, write the function in factored form. Once you have your list of possible rational zeros, how do you find which one actually is a rational zero? By substitution, and what are you looking for? Which one makes the function equal 0? Once you find that first one, you use synthetic division to factor the polynomial. The thing that drives me nuts is when people answer the B part, 2, -1, and 7. Well, 2, -1, and 7 don't multiply together to give you that third degree polynomial. That's not what factor means. If you find out that -2 is a zero of a function, then what's one of its factors? Now, if -2 is a zero, then what's one factor? What could you set equal to 0 that would give you negative 2? X plus 2. And if it turns out that negative 7 is one of the zeros, then x minus 7 is one of the factors. So the B part, the answer is going to look like f of x equals x minus something times x plus something times x minus 7. It's got to multiply back together to give you the original function. The C part will just be numbers. The zeros of that polynomial may be 2, negative 7, positive 4. I'm just making up stuff, but that's what the C part will just be numbers. The most common mistake on number 9 is leaving it blank because folks don't realize it's the same thing as number 8. I just didn't break it down into A, B, and C part for you. You have to find the possible rational zeros, substitute until you find the first one that actually makes that equation equal 0, and then use synthetic division to break it down further. But 8 and 9 are the same thing, different directions. Number 10, what's the shape of the graph in number 10? Parabola, and specifically concave down. It's y equals x squared, so it's concave down. Number 11. What about number 11? What shape is it? Parabola that opens, it's x equals y squared instead of y equals x squared. So it opens to the right. Number 12 is definitely what? An ellipse, because both variables are squared with different but positive coefficients. Number 13 is definitely a hyperbola because one of the coefficients is negative. Number 14, what about number 14? It looks like a circle, but here's the main reason I wanted to pull this up. And I thought I had one on the practice test, and I don't see it. But we talked about it in class. If it looks like a parabola, it's a parabola. If it looks like an ellipse, it's an ellipse. If it looks like a hyperbola, it's a hyperbola. If it looks like it's a circle, then you better check the radius, because if the radius is 0, it's actually just a point. And if that coefficient, not coefficient, but if that constant on the right-hand side turns out to be negative, then the radius is an imaginary number and it's no graph. All right, so if I was going to real quick add 2 problems to that practice test, and this is the last thing, I'll let you go. If I was going to add 2 problems to that practice test, I would say identify let's say x minus 3 squared plus y plus 4 squared equals 0. What is that? It looks like a circle. Both variables are squared with the same positive coefficient. But if it's a circle, its center is what? 3, negative 4. And its radius is 0. That's where I know it's just a point. The only point that satisfies that equation is the center, 3, negative 4. And then if I gave you x minus 3 squared plus y plus 4 squared equals negative 1, then again, it looks like a circle with center 3, negative 4, but what? Why can't you just divide both sides by a -1 so that you have that +1 on the right and then say it's a hyperbola? Why wouldn't it be a hyperbola if I divided both sides by -1? Ooh, that's it. Good job. Both the x squared and the y squared would have negative coefficients. Hyperbolas only have one of the square terms having a negative coefficient. All right, y'all know my office hours today and tomorrow, and the tutor center's open 8 to 4:30 today and tomorrow. Do well on those practice tests so you can do well on the real thing.